Hello, everyone, and welcome to Iron Beetle, a show where we look at the Target Beetle database, a database which is implemented in Zeek, which is rather unusual in that it assumes that the disk kind of fails and actually recovers after disk failures, a database that is written in somewhat unusual coding style called Target style, which includes unbelievable things like, not actually allocated memory. Like, you gotta code the entire database only using the memory you have allocated at the start. So where we are at, I think we've covered the bulk of the database at this point, and right now we are like sending off the areas which we haven't explored during our first read through of the code, and a particular big area which we are yet to explore is Whopper. Or rather, I think we've started looking at the Whopper 3 weeks ago. And then we had two bonus episodes, one with Toby, where we discussed loser trees, and another one is like a Russian language podcast about everything Target Beetle. Okay, so that probably means that it would be smart to remove my armchair from the frame. It would be smart to start with drawing some pictures to reconnect with the Whopper, so to say, to understand again how everything fits together. Okay, so let's open our Excalibur. Hopefully it will work. No, I actually want you to be full screen. Okay, this is annoying. No shortcuts work on this operating system. Okay, so the Whopper view stamp replication operational something. Actually, I don't remember how the Whopper is decoded. So probably if I share my screen, it will be easier for you. Okay, yeah, this is better. Okay, so what is the purpose of the Whopper? What is this thing? The purpose of the Whopper is to simulate your entire cluster so that you could debug issues which involve more than one machine. So let's think how we might do this. So normally our tiger beetle is a cluster of 6 replicas. So let's try to draw 6 different machines. So 4, 5, and I'm running out of colors. So okay, let's do the shaded one maybe. Okay, so these are our 1, 2, 3, 4, 5, 0, because we of course number replicas from 0. So these are our 6 replicas, and actually, if you think about, like, in the real world, each is a dedicated, separate computer. Like these rectangles actually are somewhat spread out from each other. So this one is here. This one is here. And there is actually some network back and forth going between them, and that is the system which we want to simulate. And well, how would you do this? There's actually many different ways how you could slice this into manageable chunks, but useful thing to do is to think physical versus logical. This is like super important. Can I color just part of the phrase? Okay, no. So let me do this this way. So no. I want this to be black, but I kind of like want to emphasize the difference between the two. So physical is blue and logical, let's say, is red. So what we are going to say, there is a continuum. So we'll start at a physical simulation, and then we'll move towards the logical simulation. So okay, how can we start at the physical level? Well, the first level we can do is that, just run the true cluster. Like, really, just don't try to simulate anything. Like, take production cluster, deploy some binaries, and you got yourself a simulation test. And if it fails, well, you found a bug. The problem here is, of course, well, first of all, it is production cluster. Like, we would prefer for it not to crash. And the second problem is that it's kind of like hard to reproduce, hard to match. So the second level would be automatically provision test clusters with Docker Compose, Kubernetes, or something like that. So, rather than like having like one production cluster, like, the testing cluster, you have some script somewhere which you can run, which will go to Amazon, rent 6 machines, and provision this cluster, maybe submit some synthetic workload. So this is kind of like nice in a sense that this at least gives you reproducibility of a setup. You could easily rerun the test. But the problem here is, well, first of all, you need a lot of computers. Like you need to spin up virtual machines, and there might be like, failures in this distributed system unrelated to failures in the system under test. Like, you're trying to spin something, you try to run the test, you try to spin machines up, and machine just isn't there, or something like that, which would be pretty unfortunate. So the second problem there is that the actual failures aren't going to be easily reproducible. Like, there is like a lot of variation in timing of the real machines. So if you rerun the same test with the same inputs, you kind of like might get different results. So the third level, and this is kind of like so far this is kind of like still all is physical. Can I somehow rotate this? Yeah. No, I don't. Yeah. So this is kind of like physical, but we are getting a little bit closer to logical. And the third step is still pretty physical, but it is kind of like much more tame. And this is run Docker Compose on a local machine. So you have this setup which actually spins up your distributed system in a reproducible way, but if your system is coded in a good way, there isn't actually anything requiring this thing to be fully distributed. So you actually can like go and spin up 6 virtual machines on the same physical machine. And that would be massively more convenient, but still it probably would also be more reproducible because, like, latencies on a local machine are more predictable. But still, I mean, you need a big laptop for this because, like, you're spinning 6 copies of a real production database. And failures would still not be perfectly reproducible. And it would be somewhat hard, like, because you are now running this on a local laptop, you actually have the opposite problem, that your network is now almost perfect. Your disk is almost perfect. So, like, the time synchronization is ideal between different virtual machines. So there isn't enough failures. And you would have to, like, hack something into reproduce failures. So the next step to kind of, like, make this less physical and more logical is to say, okay, now let's do this run each replica in a thread in a process. So this is actually I mean, okay, let's. It's not actually red, but it is getting logical. It is orange now. So the idea here is that, okay, kind of like so far we like assume that like a replica is a full POSIX process, but probably it wouldn't be too hard to take a system and kind of like run many instances of the system in the same process. It doesn't necessarily mean that, like, every system runs on a single thread. Maybe you need, like, multiple threads for each system, but still kind of like, if you don't rely on like absolutely horrible practices like global variables or whatever, like, not just like singletons, but actual, like, static global variables, then it should be fine. And at this point, the system becomes like significantly easier to test. like once you get to a single process, then you don't need special script to spin stuff up. You don't need a big machine. You can just run. This is basically your normal test. So you took a distributed system and made it a normal program. Still, this is kind of like not really great because this is still physical. You kind of like essentially you don't change anything about the interface of your system. Your system still assumes that it is just a process running somewhere on a machine. It's just that you fake the API of a dedicated physical machine within a bunch of threads in a single process. And the biggest downside here is that still you depend on the timings of your thread scheduler for testing. Your failures are still not reproducible. They are the most reproducible failures of all these scenarios, but they still are far cry from being reproducible or from being minimizable or from being, well, is it actually, at this level, you also could do some amount of fault injection, but still we can do better. And let's get to the physical. So to the logical. So what is the logical step? Replica is an explicit state machine. Cluster is a composition of state machines. This is kind of like a big change in thinking, and even bigger change in how you write your system. But I think this actually yields a system which is much faster to test, and that means the system which is much easier to test, much easier to debug, and a system which you can test much more thoroughly because you could run more and more tricky tests. So basically, this is like, big galaxy-brained insight. Concurrency is just state machines. That's it. Like, you probably learned about state machines, I don't know, on the third week of your intro programming course, because like state machines are like super simple of an idea. You don't even have to write some kind of a code. It's just, there's like state, there is arguments, and you modify the state. Like everything is a state machine. And this is in contrast to concurrency and parallelism, which you probably learned somewhere in the master's course rather than in the bachelor's course. Because, well, at least that was for me. Because yeah, state machines were like one of the first things I learned, and concurrency and parallelism were one of the last things I've learned. But the thing is, if you think about concurrency, what concurrency is really just state machines. And the only trick of concurrency is that the state machine is non-deterministic. Normally, you think about the state machine as it accepts inputs one by one, like regular expression munching on a string. You get a letter from a string, one letter at a time in a very specific order. But that doesn't need to be the case. You could also imagine a state machine which actually at any given point in time has a bunch of inputs, different state transitions it could take, and which at any given step takes an arbitrary transition rather than going through them in any particular order. And that is basically concurrency, just state machines. And if you think about it, and you apply some algebra, you immediately see that if you have one concurrent system, which is a state machine, and another concurrent system, which is a state machine, you could actually, it's not even a composition. It is just a straight out product of state machines. You can just like take this like two states and two state transition functions and just like jumble them together and say that for this new state machine, the input is a pair of inputs and like the state transition is like a function which operates on the pairs of state, and that's it. And this is brilliant. So now you can run this thing on a single core, and you can get full control over all interleavings. So you actually could select which machine you want to step through and which inputs, which you can select at random, you are going to feed into the state machine. You get very fine-grained control over fault injection, because now if you code this as an explicit state machine, then all the inputs are just events which you feed in the state machine. And if you modify the input events, you actually can model arbitrary faults. So this is how Whopper actually works. We are at this logical level. We think about our replica as a state machine, we code it explicitly as a state machine, and that gives us very powerful single-threaded simulator. Okay, so without further ado, let's actually jump into the meat of the code. Let's see how this thing actually is implemented. Okay, so hopefully you can see the code, and yeah, let me stop blinding you with live theme. I probably should switch my Excalibur to dark theme as well. Okay, so this is Whopper. This is me. We've seen this before. Actually, this is to do from last time we looked at Whopper, and I think this to-do is actually fixed. So let me quickly refresh. Okay. Yeah. You see, used to leak in our Whopper. Now we don't leak, but this is not interesting. Okay. So what I wanted to show is the main loop, which is really simple. We just call simulator.tick. So everything that happens happens inside this method, and this is like stupid single-threaded program. There is no actual real world grown up concurrency with threads or async await or whatever. This is just straightforward function A calls function B kind of code you learned to write a long time ago. Okay, so the main thing we have in the simulator is the cluster. So we are going to look at the cluster, and here actually I usually kind of gloss over this Zik style generics, which are just functions which return type. But here for the Whopper, it actually makes sense to take a closer look at what we are doing here. So this is cluster, and this is how we instantiate our replica. And remember, our replica is generic, which takes a bunch of parameters. So it takes a state machine, which contains double entry bookkeeping logic. It takes a message bus, which is the networking layer. It takes the storage layer, which mediates access to disk. It takes time, which mediates access to time. And there is append-only file, which is kind of extra thing we don't need to cover today. Basically, extra plugin for disaster recovery. Okay, so what are we instantiating our replica with? Well, for the state machine, we just pass in the state machine, and we got a parameter, so we can instantiate our cluster with like any state machine. And in the code, we have two. We have account state machine, and we have the testing state machine, which is just a simple key value. But then we pass storage, and the storage is test storage. So we are in the testing folder, and inside this testing folder, there is like test and storage, which is, yeah, here it is. And this is different from our production storage, which is in storage, which is like in the top level. And similarly, for the message bus, we also use message bus from the testing folder rather than production message bus. So this is where, like, you know, the magic of dependency injection, the mocking, if you like, happens. This is where we kind of like take out the real things and put fake things into their place, but they are not really fake. They are like they implement the full interface, the full contract of the actual network card and disk-based real implementations. Okay, so this is what happens in terms of the types. In terms of the values, we have an array of replicas and an array of storages. And storage is kind of like, is going to be rather important thing, because most of the inputs is going to be driven by the storage. So when we initialize this thing, yeah, you see that we initialize each storage with a testing storage, and then we initialize each replica somewhere. Somewhere we initialize each replica. We initialize each replica, and we pass storage. Oh, okay. So replica open is actually a helper function. So if we go to the helper, then we call replica open, and we pass storage. And I think replica should be holding storage by pointer. Yeah, this is by pointer. So, okay. That is kind of like starting to make sense. So we're actually running everything on a single thread as an explicit state machine, and there is a bunch of replicas, a bunch of storages, and we are going to step through storages. So let's see how it works. So let's get into the middle of things. Let's say that we are in some LSM tree. And we want to do some asynchronous operation. We want to read something from disk. So there is going to be a bunch of setup, but eventually, yes, we are going to call read block to read the block. And that after, okay, I'm lost. That after a bunch of flavor checks, which we've covered before, is going to call storage read sectors. And I think we've looked at the production implementation of read sectors, where, like, you know, we actually go to our IO uring and enqueue the syscall for the kernel to make for us. So let's actually see how this works in the testing storage. Testing storage read sectors. So the same function, the same signature. And here actually, like, we rely on duck typing of generics pretty heavily here because you see, like, we don't actually ever like explicitly define interface of storage, and you could do it in Rust, but actually it's going to be like pretty nasty because, like, there is storage and it needs to implement some trait, and, like, we actually use like this storage read, which is like, a different type. So you need to like do associated types, and then you need to implement like types of traits, and like you could do this, but it's like, a lot of overhead, a lot of mental indirection, which makes code somewhat hard to understand. So for us, we just say kind of like, yeah, without anything, like, just do this directly. This, of course, is like pretty horrible if you then ask someone else to use this code in the library, because if you're using something in the library, you want to read the API documentation, and to read the API documentation, you actually do need to have the API spelled out. But this is not the context in which TagBittle operates. TagBittle is not a library. TagBittle is an application. It is a small application which is developed by the team of full-time developers. So we don't need to explicitly read the docs, because we just know these interfaces. We work with them every day. So for us, the drawback of not having an interface for the reference is not that important, but the benefit that, hey, actually we can write direct code and not go through the mental overhead of like trait dispatch is important. Okay, so which one is this? This one. This one is this. Okay, let's see what we are going to do here. We are going to verify that, hey, this operation is correct for the zone, and then for superblock headers and prepares, we are going to verify that we are not going to read an initialized memory, that the memory we are reading is initialized. And again, this is, as you see, this is already the place where if you went with like physical simulation, you will have trouble, because on the physical level, it's kind of like hard to say which stuff on disk is written to and which is not written to. And on a logical level, I mean, it is super easy. You just maintain like bit set of like written sectors. Okay. Then we, as usual, save all the information about asynchronous operation in the context. So another typical TagBittle Zig pattern, that this is asynchronous operation. So in a normal language, what would happen is that you would allocate some sort of a closure on a heap, which would store the information which is needed to resume this operation when it is ready. Like in particular, you need to store the buffer and the offset. In Zig, we don't have closures, so we have to explicitly stuff this data somewhere. And that somewhere is the context, which is this read object itself. So the context here is that the caller allocates memory for this operation by virtue of having this storage read chunk of memory as a field or local variable somewhere. And then it just passes us this memory. So if this were Rust, this would have been maybe uninit storage read, because it actually is initialized. But well, in Zig, we don't have to care about this. Still, we do have to initialize it, and we basically let me show this side by side. We basically store every single argument. Callback, we store read is where we are storing the thing, buffer, zone, and then kind of like, you know, extra things for our logical simulation. We store a stack trace because if something goes wrong with this read, we could actually then use this stack trace to ask who called this read. Actually, okay, I mean, this is okay. This is okay. Let's go on a tangent because I'm curious. Like, you know, stack trace means that you store return address for every function in the call stack, and in general, you don't know how many addresses are there on the call stack, so you need to allocate memory. But we are not passing the allocator there. So what is happening there? Okay, so my guess would be is that Zeek restricts the number of frame in a stack. It says like, hey, you could only like do 128 frames or something like that. And there is some just bounded array inside the stack trace. So let's see. Okay, yeah, I was right. Was only off by a factor of 2. It's like 64 addresses. So that's why it doesn't need an allocator. Okay, yeah. So we actually I'm curious. How do we handle the iteration? Okay, yeah. We just treat instructions until we have next slot. I think. Well, okay, no, I mixed this up. So this is our slots, and this is our stack iterator, which like uses dwarf or elf, like whatever, to walk the stack or frame pointers. And here we basically fill everything we can fill. Okay. So we capture a stack, and then we set something called ready tick, which it's kind of like mysterious what it does, and then we do reads add. And you see, okay, what is reads? Well, reads is like just some kind of like read queue, just like a data structure, which stores a priority queue inside. And read just adds this to priority queue. So this is like actually all that our test and storage does. It just adds a read to the queue, adds it to the data structure. It kind of like, you know, function is called read sectors. Like you would think that it actually, you know, does something like maybe like reads the sectors per chance, but that's not what this function actually does. It just records your intention to read the sectors without reading those sectors. Okay, so let's see what is that priority. Well, actually, I mean, let's not play stupid games here. I think you've at this point already realized that ready tick is basically telling when this read should be ready. So this is like how we model passage of times. So like ticks is like current time, and then we add read latency, which is like a random number between our configured read latency parameters, which 3 weeks ago we actually looked at read latency mean. Yeah, so you see, when we initialized this stuff, we said, hey, kind of like there is like read latency mean and read latency mean. Okay, this is embarrassing. I'm not sure if like minimum and average value should be pronounced the same or differently in American English. So let me just say min and mean. Okay. Which is just like some randomly initialized parameters. Okay, so we have a tick when this read must be ready, and then this read queue is essentially a priority queue which stores our reads ordered by ready a tick. So if you think about it, after replica calls a bunch of read sector operations, nothing actually happens. But in the storage, we get this ready queue thing, which stores all the reads issued, sorted, quote, quote, in the heap sense, by the time when this read should be ready. Okay, so that kind of like gives us a hint, and well, you see, kind of like obviously for writes we do the same. This kind of like gives us a hint for how we can figure out where the work to read the sectors actually happens. Like we need to find the usage where we remove something from this ready queue. So let's see what is the name of the function for remove things. So this is init, dinit, reset, add, remove ready. Let's see how it works. So we take a queue as parameter, mutable because we are removing an element. We take a random number generator for some reason, and we take the tick. So yeah, presumably the tick is kind of like the current time, and we want to dequeue all elements which are ready at this particular time. So, oh dear. Oh, I'm not sure. I'm not sure if Chaitanya is watching this or not, but I bet that he will be furious. So, sorry, this is now a tangent, but basically a backstory is that this priority queue is relatively recent code, which I added, I don't know, maybe months ago or something like that, to handle like better scheduling of our operations. And the fun thing is that this is the second version of the code, of not the second version of a ready queue, but the second version of the overall approach. So my first version, we weren't using ready queue, and it was like horribly complicated. And now, and the kind of like the original, I asked Chaitanya to review the original version. He reviewed it, and then there was like a ton of bugs, and I was like super unhappy with like having like 5 pull requests reviewing this. So at some point I said to Chaitanya, hey, I realized that like I was stupid, and there is like a better way to write this. So I wrote this like priority queue, which is better. And now I realize that actually no, this is still overly complicated, and there is like much simpler way to do this, because yeah, this kind of like the problem. Like we try to schedule the time in terms of ticks, but ticks are very coarse-grained. Tick is like 10 milliseconds. And what we are actually modeling is like networking and disk I/O, which can finish much faster than within 10 milliseconds. So yeah, and this is complexity. And the answer here is like, you shouldn't be like modeling this in ticks. You should say like now ns, which is like, actual time. Okay. Oh dear. Should we cut it today? Okay. No. Okay. I will make a note here. So rewrite priority queue to use nanoseconds. We'll do it. We'll do it live next week. Okay. So anyway, the way this works right now is that we have like this priority queue, and we have a tick, and we want to get the next operation which is ready. And the problem here is that there might be many operations ready and tick, and like we shouldn't be selecting them in order. So what we do is that we select a random ready element from the queue, which I think is relatively easy. So basically, we kind of like traverse the queue and count the number of elements which are ready, and then like remove a random of them. Which is, I mean, I don't want to explain this because I realize it's like terribly stupid, and there is like much easier way to do this. Okay. I'm excited. This is a good stream. I always like streams where we find not like typos, but actually like big design issues, and this is one of them. Okay. So anyway, so we were looking for what is the name of the method which removes elements from priority queue to figure out where the stuff actually happens, and the name is remove ready. So let's see. Oh dear, I'm now feeling embarrassed because I'm going to show you the code which needs to be rewritten, but no, we'll rewrite next time. Okay, we were in the test and storage. Okay, and we have this step function where we do this remove ready call, and now we have kind of like a fork. So one thing we could look at is to figure out like who calls the step, who causes the reads to be removed from our priority queue. And the second branch of a fork is to look at what actually constitutes executing the read. So let's start with the second one, where we actually execute stuff. Okay, so we kind of like pick something to pick something to execute. And then we say read sectors finish. So you see there is nice symmetry here. There is read sectors where we start operation, but we don't actually do it. We just like enqueue it, like, hey, we want to do this at some point. And then there is like read sector finish, which completes the operation once it is ready. So okay, let's see. Okay, so we pick actual offset we want to read from. We copy into the destination buffer. So remember, in the read, we store from which zone of data file we are reading. Like, is it a grid, write-ahead log, the redundant write-ahead log, the super block? We store the offset, and we store the length by virtue of passing the buffer we are reading into and treating the length of this buffer as the required read. Okay, and you see the way what we do here is that we copy from memory into this buffer. So presumably this memory is just our in-memory representation of the data file, just slice of memory which more or less directly corresponds to the data file. And then there is like a bit set of which parts of memory we are actually reading. Okay, so after this operation, we kind of like copied our memory. But then you see, as I've said at the beginning, Typebiddle doesn't assume that the disk is correct. Typebiddle assumes that the disk can return error. And the hard thing here is that, yes, disk can return error, but if you're looking only at a single computer, it will take you a lot of input-output operations to actually hit this error. Like it takes a lot of time for this to actually fail. So like if you just naively try to handle this error, your code will be wrong because your handler will never ever be called in testing. So we need to amplify the probability of a failure, and this is exactly what tested storage allows us to do. It allows us to, like, after we have copied like the pristine data into the buffer, to flip a coin and say, okay, let's fold this, and we kind of like pick which sector we want to fold, and okay, so what do we actually, oh, okay, yeah, right. So this is just a login. The actual logic here is just setting this false a bit. So okay, actually, okay, actually, I don't like this, because we fault sector, so it is faulted, and then it remains faulted. So we don't clear the fault, which is kind of like we our faults do not clear by themselves. Is it actually true? Okay, so how is it called? Faults set and set. Oh, This oh, okay. This is mission failure mode. We should allow storage faults to heal. Okay. Well, anyway, basically, the main things are, like, okay, repairing faults is like extra level of test of fault injection, like, where you like, level 0 is you don't inject faults. Level 1 is like, you inject faults. Level 2 is like you inject faults, but then you repair them, which also can happen. Which we, I think, don't do. Maybe I'm misreading. But okay, let's keep it level 1 where we inject faults. So, like, we flip the coin, and if the coin says that we are unlucky, we go and fold the sector. So then we go through the sectors of our read range. So remember, like the actual API is like the POSIX read style. So you pass a buffer and you read this into a buffer. But actually, all the input, like, disk is a block device. You cannot write a single byte to disk. You always write a sector. So that's why internally we model this in sectors. So we kind of like take this read and then we slice it into sectors. And then if we want to corrupt a sector, like, we go and just flip the byte in the sector and, like, apply misdirects and then finish reading. Okay, so that's actually what would you expect from a storage which models disk and memory, that you store the actual data in memory, you copy it, and then you fault inject the data by corrupting the buffer. Okay, so the mystery remains, like, who calls the step function? And here we go back to the cluster. And you see that in the cluster stick, we interleave steps of all storages. So this is driven by the tick function. And cluster tick, in turn, is called from, it's called from the Whopper tick, but I realized that I forgot to show you like the main thing, like what actually does it mean to like execute the read, because we corrupted, but what actually happens then? And then we invoke a callback. So this is kind of like the part where we say, okay, now something else happens, and this is the callback which we've seen in the grid. So when we call this callback, we are going to get back into the replica. And yes, this whole thing is driven by the tick function in our simulator. So going back to main, the loop of our simulation is the tick function. So during the tick function, some callback gets invoked on the replica. This callback causes the replica to do some things, like send messages over the network or like access the disk. We haven't looked at the network, but it works more or less the same way. This callback causes replica to call read sectors like, I don't know, 10 times. And these operations are going to add reads to the queue in the storage, in the test and storage of a replica, but they wouldn't be immediately executed. And then we'll continue ticking. And once we tick to the point in time where we should be executing those reads, that, well, we dequeue it from the queue in the step function, and we kind of process the read, and then we call the callback. And then the replica gets to run again, and it will again do some other like dependent reads from disk or writes to the network or whatever, which again will add to this queue, and that way we will be ticking. So coming back to this picture, what we actually have here is non-deterministic composite state machine. Let's make this big because it is important. So we have these bunch of logical state machines. And they are like parts of composite state machine. So this whole thing is a state machine. And then we have this queue, okay, which is actually heap. Okay, let me draw it as a heap. So this is a heap heap of events. And like this is like event which is called I don't know, read sector 1, and then maybe there is read sector 2, and then maybe like write sector 1 again, like why not? And then on every step we take a random event from this heap, and we feed it into the state machine. And this is how you do logical simulation of the entire distributed system with many participants, with many replicas, with many clients on a single thread, on a single laptop, which runs really, really fast. Okay, so I think we are going to stop here today. And next week, we are going to revisit this whole thing by rewriting the implementation for the third time. Because I messed it up the first time horribly. I messed it the second time. Well, I thought I did it good the second time, but now I realize I messed it the second time as well, and hopefully third time a chance. Okay, so in a week, -1 hour, that is on Thursday at 5 p.m. UTC, we are going to operate live on this Twitch stream, and then on the recording on YouTube on a Whopper to make it better. See you next week.